Now, let's talk about our third section on this unit, which goes all over mass and electrons. So now the vocabulary for this section, we'll be talking about these terms, and you'll be more familiar with these by the end of this video. They are atomic number, atomic mass, isotope, average atomic mass, valence electron, alkali metals, alkaline earth metals, halogens, and noble gases. Now, let's start with a little bit of review of the things that we've talked about so far. So just very quickly, we know that in this periodic table, we have these blocks where we have all these different elements, and it's telling us the specific information about each element. And so just so we're able to read through these blocks in the periodic table, we know that on the top left, we have the atomic number. In the center, we have the symbol, just the 1 or 2 letter abbreviation for each element. And then underneath that, we have the full name of the element. The atomic number tells us the number of protons for each atom. Remember that the number of protons, this is a defining characteristic of each element, and the periodic table is arranged in increasing number of protons. But what we'll learn in this section is that the atomic number also tells us the number of electrons. I'll tell you more in a second on this. And then finally, at the very bottom, we have the atomic mass, and this is both the protons and the neutrons that are found in the nucleus of every atom. All right, so let's start talking about atomic mass. So remember that atomic mass, you get this from the protons and the neutrons in the nucleus of each atom. These are the two weighted particles that we have. Now we can have isotopes, which are different versions of the same element. They're the same element because they have the same number of protons, but what's different about them is the number of neutrons in the nucleus. So this gives us a different mass for each different isotope of an element. So the way to read this, I can have two different isotopes of nickel on here. We have nickel 58 and nickel 60. And what these two isotopes is telling us is that we have the element name of nickel, so we can go find that on the periodic table. I've already pulled this on here for our convenience. But first we get the element name, so we know what it is on the periodic table. And then the number that we get, it tells us the total number of protons and neutrons. Now, if we know where nickel is on the periodic table, we can see that its atomic number is 28. So from that, we know that both of these nickel atoms will have 28 protons. There's no other way around it. If it had 29 or 27, then it'd be a completely different element. But because it's nickel, it has to have 28. Now, what can be different on this one is the number of neutrons. So again, we have different masses for these. We have 58 and 60 for these two isotopes. We know that each of these will have 28 protons. So really, the rest of the way to get to 58, that will be all neutrons. So we can use this formula to find the total number of neutrons when we know the mass of the element and we know the number of protons. So if we just take mass and subtract the number of protons, we get our number of neutrons. So in this first example, we know we have 58 total mass for our nickel atom. We know we have 28 protons, so just take 58, subtract 28, and you get the result of 30. So in this nickel 58 will have 30 neutrons. And then we can do the same thing to our nickel 60 example isotope. And so we can take our 60 mass for our nickel 60, subtract the 28 protons that we know from the atomic number, and we get the result of 32 neutrons in this isotope of nickel. Now, I know that in that example we had before of nickel 58 and nickel 60, we assumed our mass to be this whole number. There wasn't any decimals that went into it. And the reality of that is that that's really just a simplification. It makes our calculations a little bit easier, especially when we need to know how many protons and neutrons are in an atom. But in reality, we have these more specific measures for telling the masses of our different elements. And so you can see that on here for this potassium element, you can see that its mass will be 39.098. But the question is, which isotope of potassium will have this mass? And the truth of it is that none of the isotopes of potassium will have this mass of 39.098. What this is actually the average atomic mass. And so it's an average of every naturally occurring isotope of potassium. So now the average atomic mass, it tells you every naturally occurring isotope of an element. So there are other isotopes that are radioisotopes. They decay, they fall apart into smaller elements, but those aren't counted in our average atomic mass because they all exist for different amounts of time. So it's not a very accurate way of saying all these different isotopes will add on to our average. Now, some isotopes will be more common than others, and so this average atomic mass actually shows you how common they are. So there's a formula that we can use for finding the average atomic mass and taking into account that not all atoms, all isotopes are as common as others. And so the way we do it is that we take the mass of an isotope and it is multiplied by its abundance, how common it is, and then we add that number to the mass of the second isotope multiplied by its abundance, how common it is, and taking the result of as many isotopes that are naturally occurring gives you the average mass of that element. So now let's do this example where we have two different isotopes of an element. This first isotope will have a mass of 84.9118 atomic mass units, and the second isotope will have a mass of 86.9092 atomic mass units. Now, how common they are is that isotope 1, you can find it 72.15% of the time. And for isotope 2, we can find it 27.85%. But we can't use those numbers in a calculation like this. So we need to take our percentages and convert it over to decimals. All you do is you just take the decimal place that we have in our percent and shift it over 2 places to the left. So 1 and 2 are 72.15% becomes 0.7215. And our 27.85% becomes 0.2785. So now what we do in this case, we just need to multiply our mass multiplied by that decimal abundance that we have. So in this first one, 84.9118 multiplied by 0.7215 gives you the result of 61.27 atomic mass units. And in the second isotope, 86.9092 atomic mass units multiplied by 0.2785 gives you the result of 24.20 atomic mass units. And then all you'd have to do to get to the final average atomic mass of this element, you just add these two numbers together. So if you add 61.27 plus 24.20 atomic mass units, you get the result of 85.47 atomic mass units. Now let's go ahead and talk about electrons. So what we know is that all atoms are electrically neutral, and this is because the number of positive protons will balance out with the negative electrons. Remember, these are both charged particles, but electrons have a charge of +1. No, I said that wrong. Protons will have a charge of +1, and electrons will have a charge of -1. And because they match up, they cancel out each other perfectly. Because in a neutral atom, the number of protons is the same as the number of electrons. This is why when I said earlier that our atomic number tells us the number of protons, it also tells you the number of electrons, because in order to be balanced and electrically neutral, these two numbers always have to be the same. Now, if you remember where the electrons are found, they're not inside the nucleus, right? They fly around the nucleus in these orbits, and we call those the energy levels. So remember that these rings around the atom, they're dotted in this one. These are our different energy levels. And in this case, we have two different energy levels. We have the inner energy level, and then we have the outer one. And so you can thank Niels Bohr for this. So we named the model after him, the Bohr model, where we have these different electrons that are flying at specific energy levels and specific regions around each atom. Now, let's talk about a special type of electrons that we can have. And really, the only thing that's different about them is the placement of electrons on which energy level or which orbit we find it in. So these are called the valence electrons, and they're just the electrons that are found in the outermost orbit. So if you can think of kind of like an onion applying to these atomic diagrams, we have this inner layer. This is our first energy level, and then there's another one outside of it. This this would be the second energy level, and we can keep building up, 2 energy levels, 3 energy levels, 4 energy levels, really just depending on how many electrons we have to fit in into this atom. Let's see. So as you can see, the 2 electrons that I have on the inner ring, these are not valence electrons. They're just normal, regular electrons. But this single electron that I have on the outside ring, this is the outermost ring, this is what we will call a valence electron. So in this lithium, it has 3 electrons total, 2 of them not valence. That last one goes in the second ring, and that is called a valence electron. And this carbon atom, same thing. I have 2 rings, 1 and 2, and the ring on the inside, I only have 2 electrons, and these are not valence electrons. Then in the outer ring, I have a few more. I have 1, 2, 3, and 4, and those will be called valence electrons, just because they're on the ring that's on the outside. Now, these valence electrons, we're just talking about them in their location and how many we have, but these will be more important when we're talking about bonding in Unit 5. And it's these valence electrons that determine all of our chemical properties. And it's for this reason that a lot of elements in the same family or in the same group, they all have the same number of valence electrons. And for that reason, they have very similar chemical properties. Like we saw with the sodium, the lithium, and the potassium, these are all metals that are in this group 1. So here we have lithium, sodium, and potassium. And you saw they all react very similarly in water. So now, the groups that we really focus on, notice that I have a big blank space here for the transition metals, and then another blank space here for the lanthanide and the actinide series. The reason we're not counting those is because they have really weird bonding, and it's a lot harder to predict it. So we're just going to not worry about it. We're not going to look into it. We're just going to worry about the main group elements, which are these 8 columns on here. And really, from that, you should know that anything that falls in this first column, this is group 1, it will have 1 valence electron. That's what I'm showing on this graphic. In this second column, column number 2, they will have 2 valence electrons. In the third column, skipping the transition metals, we skip to this third column, and this will have 3 valence electrons, and we'll continue the pattern. In the fourth column, this will be 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and 8 valence electrons in this last column, with the exception of helium on this one, because helium doesn't have enough room for 8 electrons. It doesn't have a need for 8 electrons either. Since helium only comes with 2 protons, it only needs 2 electrons. So that's the max for that. Anyway, but the groups that we focus on by name on this specifically is the group 1 elements. These are the alkali metals. Remember, these are the ones that come in this first column, and they all have 1 valence electron. That's why they all have similar properties, because they have the same number of valence electrons. Then in the second column, we get to the group 2 elements. These are the alkaline earth metals, and these all have 2 valence electrons, and again, very similar properties because they all have 2 valence electrons. Then we're going to skip over 3, 4, 5, and 6. We're not going to focus on them too much until we get until 7. So these are the halogens. So these are things like fluorine, chlorine, bromine, and iodine, and even acetine, but acetine isn't used that often. But these are the halogens, and these all have 7 valence electrons, and these will be very common when we're talking about bonding and different types of compounds that we can have. We'll see that we can have a whole group of compounds that are just for the halogens. So we'll see that more in Unit 5. And then finally, this last column, the number 8, these are called the noble gases, and these all have 8 valence electrons. And I'm going to tell you a little bit more about the noble gases, why these are important, why these are special. All right, so now we're finally getting into the noble gases. So let me pull up my graphic again. We can have the full periodic table. The noble gases are going to be that column that is all the way to the right. So it's going to be helium, neon, argon, krypton, xenon, and radon. All right, and so they're group 8 of the periodic table. They're the rightmost column, and so because they're group 8, we will know that they have 8 valence electrons. And so actually, the number 8 is really special when it comes to the periodic table, because when we have a fully filled orbital after the first one, when we start in layer number 2 and beyond that, they can only take 8 electrons at a time. This is the maximum number that we can put in an orbital, so it'll be 8 electrons. Here they are all counted out for you from 1 all the way to number 8. This will be the maximum number that we can put um, in the orbitals. And the reason for this, it's well, not really the reason, but the explanation for that is that it's called the octet rule. We can only fit 8 electrons in an atomic orbital. Uh, and now, because they have a full octet, they have the maximum number. That means that they don't take part in any chemical reactions. So the noble gases are not reactive, and it's this feature that helped us to organize the periodic table. We said that the noble gas would be the limit on the right because they don't react. This is where we start over in the next energy level. This is where we start over with our valence electrons. This is where we start to get chemical reactions again with the elements. If you're following along in order, going from hydrogen to helium, lithium, beryllium, and then neon to sodium and magnesium. So think like that. So we'll be talking a lot more about this in the next unit when we're talking about chemical bonding, what happens in a chemical bond, and how these atoms can change during a chemical reaction.